Okay, I think we can start since we're a few minutes late. I don't think I'll cover the whole hour and a half for this, so you'll have some time to play with things. But so in our last few slides, we were talking about some ways of optimizing code, and I kind of struggled a bit again, like I said, with this, saying that because the code that we're working with in the class wasn't so in any need of much optimization, but also everyone in this school is working on very different projects that are not necessarily the same needs in optimization. If you're really an expert and you're doing things with GPUs, that's very different than someone who wants to maybe run a small study on their laptop versus someone running on a cluster with thousands of jobs or something like that. So it's very hard to come up with a comprehensive guide to everything. I had some slides originally on like parallelization and other methods, but I took them out because I think they're too detailed for what I'm going to show here. This is already quite detailed. But if you have questions about those sort of things, I can of course answer them later on. So what I wanted to show now, if I can find where my window is again, here it is to go back to this profiling example here. So this last time we looked at this, we were looking at this cutout of this supernova remnant image, and we ran. I showed this very naive implementation, and we showed that it was, a bit slow because it takes 5 or 6 seconds to run. And by the way, it takes 5 or 6 seconds to run now, but that's why I cut out this small piece of the image. If you actually run this with this full image, which is not that big, 1,000 pixels by 1,000 pixels, that's, on the web, that's nothing, right? This code takes like a minute or something like that to run. It was sort of a pain to do the demo if I have to wait a minute every time I click. So this code is quite inefficient, right? So this is a case where I would want to do something better. And so what I'm going to do is to show you a method that I've used to, just sort of methodology that I've used to compare a bunch of different implementations that I've made of different functions. So here I re-implemented this a few different ways, and I want to make a nice comparison of them. This is maybe a bit more fancy than you would do in reality, but I think it's a nice way to demonstrate just the differences in performances. And so what I'm going to do is use a special feature of timeit. I'm going to just show you here for a moment here. You remember this timeit function? Let's say timeit, sine of range. Or no, do we have math here? MDB dot sine of, I don't know, np dot a range 100 or something like that. That gives you a result, as we saw before. But what if I want to store this result and actually do something with it? One thing you might not know in Jupyter Notebook, so wait till this runs, maybe I should make something a bit smaller. See if we get an answer. Yeah, okay. So you have this nice printout here, but you want to actually store this information somewhere. If you look at the docs here, by the way, in Jupyter Notebook, if you hit Shift-Tab on any symbol, you'll get the documentation for it. So like if you want to know what A-range does, hit Shift-Tab on it, and you see the documentation. Timeit has some options so timeit is not actually a Python function, but also it's a Jupyter magic function here, but it has some options here. And one of the options here is, somewhere here is O, which will return a timeit result object that can be stored in a variable to inspect the results. So if I do timeit-o, that, you'll see the output of the cell is now, let's see if it works. This looks a bit weird because this is not actually Python code. This is the Python code, but this is some Jupyter magic. But not only I get the printout, but I get back some object called timeit result. And I can assign that to something like that. I'll call it result. Okay, I think I should run this again. And by the way, one of the other options is to tell timeit to run fewer times automatically. So if you wanted this to do less statistics, you could give the option to make it only run 5 times or something. And now if I look at this, make this result object, it's some sort of class. It has some, if I hit tab to complete things in here, it has some attributes of it. And so it has things like average, which is, I think it's in seconds, the average times, that's this 1.82 microseconds, so that's actually here in seconds. And you also have resonance dot, I think, best, and that's the best time of all the loops, and then you have the standard deviation. So that's basically where it printed out these things here, right? So it did something, the printout, it turns the seconds into nicer units like microseconds and nanoseconds, but you have all the information there. But also, I think it also has loops, this is how often it ran it 1 million times, this particular function. So you can inspect all this information. Some of these other things actually don't know. Compile time, I don't know what that means exactly. this case. Somewhere there's documentation on this. If you give it help on time at result, yeah, okay, so if you give the help, also in Jupyter or in Python, if you give it a question mark or use help on something, it'll give you the help not as a pop-up. And you can see these are the attributes. Compile time is this time of the statement compilation, I guess by the Python compiler, because these are not actually compiled statements. Anyway, so that lets me collect some information. So what I'm going to do is create a dictionary called perf here, and that's why I'm going to store the results of different trials. So here is my smooth loops function that I had above, and I'm going to set perf loops to equal this time at dash O now of that. So let's run it. By the way, you can see that the cell is running. It shows a little star when the cell is running. That means wait, for it to finish. And of course, it's not a very fast function, so it's probably going to evaluate it about a few times, so it's going to take at least 10 seconds or so. So it took 3.62 seconds on average. And now I have this perf object that has, it's just a dictionary, and I called it loops, so I have loops in the time result. So now if I do like perf loops, and I can do dot average, I have the information stored. So I'm going to build up this as I go, and that's just sort of a nice way to do this. This is one. There's many ways you can do this, but then here you can ignore. This is just some plotting code. I made a plot code that plots the speed that basically takes that perf dictionary and makes a nice matplotlib plot, either as absolute or as relative to the first element. So you don't have to look at this, and then I have a plot performance code that just makes a figure and plots speed twice, once as absolute and one as relative. So this you don't need to look at this. It's just for a little setup that I want to do. So lets me do this. It makes this plot. So on the left, it shows the average execution time for loops, and with an error bar on it even. And the right, it shows the speed up relative to the first element in my dictionary, which there's only one element, so it's 1.0. So it's the same speed as loops because that's the only object in there so far. So this will help me as I try different things to make a nice little plot and compare things. So this is just for, again, for making it friendly to look at things. So then the first thing I did is I said, okay, I want this thing to be faster. I know that the loop, looping 4 over 4, 4 ranges in Python is very slow, and I know especially this ij loop is the worst one probably because it goes over height and width of my image, which is very big. The kernel is much smaller than the image, so the mn loops is a bit smaller. So I wanted to try to optimize out that first loop by using NumPy. And so again, don't worry about the actual implementation here. This is something that with your own code, you would play with different implementations, you would play with different things. So here, you have to worry how it works exactly, but here what I did is I still loop over M&N, so I loop over the kernel, but I use NumPy to store the result using in Python, you have this way of indexing a larger array to get a smaller piece of the array. So this basically cuts out my image and multiply to the same size as the kernel, multiplies them together, and then adds that to the result. And this is a way to basically do the same algorithm, but now the loop is happening implicitly inside here. This is, again, whether this is more readable than the other one, I don't know. I think it's not too bad. You can kind of see that I'm taking a slice that goes from m to m plus h, and a slice that goes from n to n plus w, and I'm multiplying that by the kernel. And then this NumPy automatically broadcasts this, to all the elements in that little slice. And then I'm looping over m and n, so I'm looking over the kernel to do the thing. So anyway, this is now another implementation. Notice it ran pretty fast, right? So even just seeing, I clicked it. So this is my outer loop. I call this outer loop. And okay, the result looks good. And let's add to my performance metric. Now let's time it. So now it's going to run that function many times. And we'll see how it compares. So already you see it ran in 5.76 milliseconds. So let's make a little plot. And we see that here's the average speed. This is a log scale, by the way, because I couldn't even, you couldn't read anything if I didn't put it on a log scale. The loops one took, several seconds, and now we're down to 10 to the minus 2 seconds. And we are 600 times faster than the original code. And actually the code is not too bad, right? I think this is fairly readable. Maybe a little bit, you need to know a little bit about, NumPy vector stuff, but it's not terrible. But then of course that bothered me. I was like, okay, I still have a loop over over m and n, and that I know that's slow in Python. So I was like, okay, let's get rid of the loops. And there's actually there's a couple ways you can do this. This is the way I tried it. It's not it's not beautiful, but it does get rid of the loops. So I had to use this special stride tricks library or a sub-library of NumPy. And what I basically do is build up, a view of the matrix that is 4-dimensional and use this add strided function. Anyway, you don't have to understand how this works, but reading this code now, it's very not obvious what it's actually doing, right? This is very opaque looking code, but in principle, it does the same thing. It even applies, a 4-dimensional sum over 2 axes and things like that. So it's I think a bit ugly, but it gets rid of the loop. And I was like, that's great. So there's no loops anymore. This is wonderful, right? So this actually surprised me a little bit. So here's the answer. Looks fine. Again, let's do our NumPy no loops. Let's do the performance measurement. And you already see that something's wrong. Wait, it's actually slower than my outer loop one. So this actually surprised me. I didn't think that would be the case, but it's still 200 times faster than the loops, but it's nowhere near as good as the other one. So it doesn't mean necessarily writing things in a fancier way gives you a better result. And I think the issue here is probably the fact that inside here we're allocating a lot of large memory and doing some things that are not very optimal. And maybe there's another way you could rewrite this with no loops, so there's probably is, that's more performant, but it actually was better to just stick with the Python loops in this case. So it was a pretty good. So that actually surprised me a bit when I was making this demo, that it's slower. So, and actually uses a lot more memory. We'll show that later. So when you do memory profiling, we'll see it's actually less efficient than the other code. So then I told you there's this magic thing called Numba that lets you just take your Python code. Oh yeah, I forgot I fixed what did I fix before? There was I had an IJ released backwards somewhere. To see where I don't remember where it was now. Well, let's see, it'll come out probably backwards still. So I took it, basically cut and paste the original smooth loops function, and I just added this JIT from Numba import JIT, and I added this JIT thing. And that's, like I said, the sort of magic. Inside here, there's though nothing special, so it's a fairly simple function, so it should work. I probably have to execute the import first, because obviously you won't know how to do it. Okay, and now if you look at, let me actually put this first here. If we look at this function itself, you can see that this is now, what's actually, this function now is actually something special. It's some sort of object called CPU dispatcher. That's actually what this JIT thing has done stuff inside here. It's compiled the code, it's done, or started to compile the code, and it's returned some thing. It actually hasn't compiled it yet, because I haven't, this is one thing that's a bit of a thing to, or a pitfall of running something like Numba, or anything with just-in-time compiling. Just-in-time means it compiles when you first run the code. I haven't run this function yet, so it hasn't actually compiled yet. The first time I run it, it will take a bit longer to run because it has to compile, then it will run it. So when you have code that's JIT compiled, it better be something you call very often, because if you only call it twice, it won't help you, because the first time it has to compile it, and compiling takes some time. In this case, maybe a fraction of a second, but it's still there. So if I was to call this smooth loop function, so notice it took a second there, but then it gave a result. But actually, most of the time in that second was it compiling the code. Now, if I was to run it again, it's almost instantaneous, because the smooth loops function is now compiled to machine language. And okay, I got again, it was backwards here. Maybe I forget what I fixed last time. It was the result was, what did I have? This should be J and I, right? Was that what it was? Yeah. Yeah, there we go. So now we got the right answer, and let's time it. By the way, this is again another thing. When you're using time it here, make sure you first run the function once if it's JITted, because otherwise time it will include the compilation step and you'll get the wrong answer. Okay, now we have 5 milliseconds. That's pretty good. Let's plot performance, and we can see that loops JIT is actually a bit faster, right? So it's like 700. Interestingly enough, when I ran this yesterday, it wasn't quite as good. I think there's some, maybe because I had this backwards even, that just changing that index actually gave a speed increase, probably because of caching, no longer could, the stride was a bit better to optimize into the CPU. But anyway, it's about the same speed, if not faster, than the outer NumPy loop. But that shows you how things can be deceiving, right? But that's nice, because that means I didn't have to know NumPy at all. I just basically wrote a loop and I magically got it. Okay, there's a lot of fanciness behind this that installs a whole compiler onto your system when you install NumPy, but it's still pretty nice, right? That means there's almost no effort. Do you have a question?
If you have the function in the package, it would be the same. Meaning that if you import the function in your own code,
Yeah.
it would be JIT. Sorry.
Yes. So if you add this JIT in your code, then when somebody uses it, magically it'll just become compiled. Again, because it compiles the first time it runs, even if they run it on a different architecture, it'll compile for that architecture. So you don't have to the nice thing about this also is you don't have to distribute binaries of your code for different architectures. If you use this Numba, it works for any Python, any CPU architecture out of the box. But you get this overhead that if you have a lot of these JITted functions, the first time you call them, it has to compile them. So the first time the person runs your code, it will compile them. There is actually an option I didn't show here. If you look at the help cache here, if you say cache equals true, it will store the compilation into a file and then load that next time. So then if you do use this a lot, on the same system, that actually speeds it up a lot. Then that means the next time you run it, if it's in your, then it won't have to compile it again. It'll just load the one that was there before. So there's some fancy options. I didn't show also, there's also other really fancy things, like you can say the target here is a GPU, and then this might not work directly. You'd have to do, GPUs have a bit extra things you have to do for memory. I think you can also do things like parallel equals true. This will probably not work. Let's just see. This is a good on-the-fly demo that I didn't think about. That will tell it to parallelize the code, but since this code, I have to tell it, I think I also have to import prange, and then I have to tell which one of these things I'm allowed to parallelize. Let's say if I do this prange here, that will now, everything in here will run in its own thread on a different CPU. I should tell you, that's a bad idea for this particular example, because you don't want that to happen. You're actually going to overwrite, you're going to have memory collisions. So let's see what happens. I think it'll probably give the wrong answer. Let's see what it plots out. Oh, surprisingly, that actually worked. I'm not sure let's see if it's actually any faster though. So that was 5.0 milliseconds. This is such a small image that parallelizing probably does not help much. Parallelizing meaning this is going to run multiple threads inside that and run each one on a different CPU. Oh yeah, okay, no, actually it's a bit faster. I would be very careful with that though. Oh yeah, so that actually gave a huge speed increase. So we're now, but again, I'd have to check that I did this. I'd be very careful when you do parallel things, because when you're writing to the same array and with multiple parallel threads, the order is no longer guaranteed. So if you were, this algorithm, I guess, yeah, it should be okay, because we're really just working in tiles, so it should be okay. But often you have an algorithm where your one loop iteration depends on the previous loop's iteration. If you parallelize that, you get completely the wrong answer, because now you have iteration numbers happening in random order. So actually, yeah, that's interesting. I didn't. So actually, maybe I should do two versions of this, maybe without the false. Let's just see what happens here. So this is the original one that I ran. I'll just store that, and then let's do one. Okay, that's the original one, and now let's put one with true. And I'll call this JIT parallel. And let's just, that gives us all these. Performance. So yeah, this, now you can see that we get an enormous, almost 2,500 speed increase from that. So that is a good example where parallelization might actually be good. Again, I'd be always very careful with using that. Oh, but one thing that's cool I didn't show. So now that I'm showing I didn't mean to show parallelization, but now that I did it, if I use this, I have this smooth loops JIT function. Now this is now the parallelized version. There's an option, there's a method of the function that should show here. Where is it? Inspect parallel diagnostics. And if I run that, it will print out the code and show where it parallelized. So, okay, I explicitly told it to parallelize this prange thing, so it shows that this section of the code will run on a different thread. And if I was to put prange here also, it would then have split it up into chunks that would send to even more processors. That probably wouldn't be faster, because sometimes if you parallelize too much, sending things to different threads is slower. Anyway, that's very detailed stuff, but parallelization is not always faster.
Maybe also have an issue with Windows.
yeah. I'm not sure this would work in Windows, actually. I don't know, because it uses a different threading model. It just uses the correct thing, but I haven't tried it on Windows. But yeah, so it's interesting. So you can see, and it'll tell you if there's sometimes it can optimize things better, or it'll reverse the loop order or something like that. I think so yeah, it's interesting anyway. Then I had another option. I was saying, okay, well, the final way I could implement this is that realize that this is just a convolution, and SciPy has a convolution function built in that somebody who's much smarter than me wrote. So I can actually reduce that entire function to this one line, convolve image kernel with mode equals nearest. And if we do that, we get the answer looking great. And let's do the performance of that. And actually, it's about the same as, actually, it's better than the loops JIT, and it's better than the other, about the same, as these three are about the same, but it's slightly better because it's not as good as the parallelization one, although I think there is a method option you can turn on parallelization in SciPy too. It's not by default turned on, there's a option, but anyway. Probably, if I wasn't really worried about speed, normally I would probably just stick with this because this is super simple. I know that I don't have to maintain the code; somebody else has done it, and it works, well. So I would probably err on the side of if the function exists already somewhere, and I would use it. But you can see that you could actually get some big performance increase if you really needed it by using Numba. And I didn't show here. You could also, it's something you can try yourself. Is take one of these NumPy implementations and try JITting that and see if it gets faster. And some of them should get a bit faster. Even like this one, for instance, probably will be faster if you JIT it because some of these memory allocation things that slow it down will get optimized by Numba. Anyway, so now we have a bunch of trials and we see that the best one is, in this case, this one. Although I would say that with a bit of a warning that parallelization is difficult, and normally you have to be careful with that and check that your results still work. In this case, it happened to be okay. The other thing this is where I would say that, okay, but could I make this SciPy one faster? Well, I even looked at the help of SciPy's convolve function. I just cut a piece of it out here. If you can try this yourself, put help convolve, but it gives you like pages of help. It says it has experimental support for the Python array API standard, compatible with backends in addition to NumPy. And this is something that I will mention in a bit, that there's other implementations of NumPy or NumPy-like interface that will do things for you much faster than NumPy even can, but they're for very specific situations. And if you set this environment variable SciPy array API equals 1, and then instead of passing in NumPy arrays, pass in, I don't know, like you were mentioning CUDA arrays for a GPU, or PyTorch arrays, or JAX or Dask. I'll mention those later. A lot of these were developed for machine learning things, but they're kind of fancier implementations of NumPy-like calculations that can parallelize onto different machines and do things very efficiently. Then automatically Convolve will use those, and then you'll probably get at least the speed, if not better, with just the standard Convolve function. And you don't have to worry about it being implemented wrong because it should work, out of the box. I also just put here for really being masochistic, to implement it in C. So this is if you have some C code library. This is actually a pretty common thing that you might have somebody had written a C code library. So here I actually just write the C. Here's some C code. It's not because this is Jupyter doesn't syntax highlight it correctly, but I just write that out to a file here. So this is just, let's write a file out. So now I have convolve.c, and then I'm going to use bash here to compile it. So I'm using GCC to compile it into a shared library. I turned on optimization because we can try it without that afterwards. But so that means GCC should make this thing fast. It'll create this libconvolve compiled version that I can use. Again, this is don't look at the details here. This is to show you that it's possible. And there's multiple ways you can call C code from Python. One really simple one is using the built-in C types module, where you load the library, and then you have to tell the library what the arguments to that C function are as NumPy pointers, etc. So again, ignore that. This is just setting up to run it. But now I can actually run my lib.convolve2d, which is a C function. Notice that the call signature is quite different because C doesn't support arrays, right? Or it doesn't two-dimensional arrays, so you have to pass in a pointer to an array, the height and the width of the array, etc. So it's a bit more complicated. Anyway, ignore it. This is just, again, to follow it, but it works, right? So now this is run in C, but called from Python. And I can time that one and plot the performance. And you see the C1 also is actually a bit slower than the SciPy one. But it's on the same order of magnitude. So my handwritten C is not necessarily faster than what the people in SciPy are able to achieve, which is also probably internally in C in some way. And here I just plot also now the final thing sorted by performance. So you can see that we started with loops, and when we get down to it, a lot of these implementations gave about the same result, and it doesn't matter that much. And again, this parallelized one actually was the best in this case, so that wasn't expected either. But anyway, that's how you might speed up some code. Again, I would err on the side of making things easy to read, but for debugging purposes later on. But it's pretty interesting that you can get a factor of almost 2,500 in speed just by changing, or in this case, just by adding a decorator to your function. Okay, so then we're going to stop there for a second, go back to the slides for a moment. Oh yeah, this is just to mention that I said there Dask, JAX, and a few other PyTorch. I'm not going to cover these here. These are very specific. Actually, JAX is quite similar to Numba in that it has a JIT compiler option, but it also does a few fancy things like it's made for machine learning people. It has one thing that's quite cool that might be useful for people who are physicists or using or fitting very complex models to data. That it can do auto differentiation of NumPy array operations. So if you have a function that calls, a function that does a bunch of stuff to NumPy arrays, it can automatically compute the Jacobian of that, meaning the partial derivative with respect to all the parameters of the function automatically in an analytical way. And so for those of you who are experts in like fitting and data processing, you know that when you fit a nonlinear model to some data, it has to evaluate the function many, many times, not just for every time it tries to move to a better fit, but also to compute the derivatives. If it doesn't know the derivatives, it does numerical derivatives. So if you have a fit with 5 parameters, it's going to do maybe 100 samples in every direction, every parameter direction. So 500 samples of the function. For every step of the fit, and the fit might then also take 1,000 steps, so it can be very, very slow if your function is slow. If you know the derivative, you can reduce the speed by a factor of like 100 times the number of, or 1,000 times the number of parameters in your model. So this can be very useful. The reason why I think in machine learning they use these models that are, in like AI, it's these models that are 250 parameters or 12,000 parameters now, a lot of them, and so being able to know the derivative along 250,000 dimensions gives you a huge speed up. For the stuff that we're doing in this class, it doesn't change much, but that's where there's some cool technologies out there that I haven't really played with too much in detail, but for those of you who are really experts in that kind of stuff, could be useful. Dask is another library that's nice for taking NumPy operations and automatically, what it does is it defers the computation. So you basically just replace, these things basically replace NumPy arrays with their own implementation that look just like NumPy arrays. But if let's say you say an array that's A, an array that's B, you say A times B, it doesn't actually do the computation A times B. It waits until at the end when you need it to do that computation. And that allows it to build up a more complex graph, I guess, of all the different operations. So that's a simple one, A plus B, but imagine that later you divide, you multiply, you do some convolutions, you do 100 other operations. It can then optimize the order in which they're run, and it can parallelize them onto many machines automatically without you even thinking about it. It's a bit fancy to set up, but then you can, if somebody has set this up for you in a cluster, I think here in Geneva, or in this, here there's a computing cluster in Geneva that's used by a lot of, or no, not in Geneva, it's in Lyon, that's used by a lot of physicists in this building. And they provide you with like a Jupyter notebook that already has this set up in it. So you can just run it and then automatically your code runs on the entire cluster without having to think much about it. So it's kind of cool. There's some nice things like this. Anyway, I won't go into the details of these, but they're more just to show you that they exist and you should take a look at their documentation and see if they're useful. And then the final thing I want to say is that for optimization of stuff, Python keeps getting faster. So sometimes just the best thing to do is just wait for the next version of Python, unless it's really important. And since even Python 3.11, they started really adding some speed up, some ways of speeding up the code. So I think in Python 3.11, you got like something like a 60% speed up for certain types of codes because they added an optimized interpreter, and each new version, they keep adding a bit more optimization and faster, operations on basic things like dicts and sets and f strings. Each time we get better, and they're now adding things for like threading, multi-threading, which is something that Python didn't do very well in the past. And so I think in the next few versions, you're going to see faster and faster optimization. So it might be that actually using something like Numba is no longer needed in a few more versions because it'll just do it automatically. You don't need Numba. And the other thing to say is that Python when we say Python, we're always talking about the version of Python you have installed here when you type Python, which is called CPython, because it's actually implemented in C underneath. But there's other actually Python interpreters like PyPy, which this one, a bit like Numba, it JIT compiles everything. And for some codes, it can be just out of the box, just changing Python to PyPy, you get a speed increase. Not always though, and if you use a lot of Numba operations, it's actually not necessarily faster, but depends on your code. So sometimes you can just change interpreters and you get more speed. So yeah, there's the last option, do nothing, wait for Python to get faster. And then the final thing I wanted to discuss is memory bottlenecks. So we talked about making speed better. And one caveat I have to say here is that I'm not sure, I think a few of you are using Windows. If you're not using the Linux, what's it called, Linux subsystem, WSL, or whatever it's called, where you run the Linux inside Windows. If you're just using pure Windows, this might not work. And it might not work even on the Linux subsystem, I'm not sure, I haven't tried it. Because this is using a package called Memory Profile, and right now it supports only Mac OS and Linux machines. So this is why, so you might not be able to follow through this part if you're using Windows. I tried to look if there's a better version of this, but there wasn't anything better. And even worse is that this Memory Profile module seems to be not maintained anymore. It works, but there's nothing really replacing it, which is kind of surprising. But for now, actually, to make sure things are all working, it was also broken in the current version of Jupyter. It breaks with the Jupyter lab for some reason. So in the environment that I created here, I pinned Python equals 3.11, so a quite old, slower version of Python. But that allows me to use this memory profiler. So unfortunately, this is something that's right now kind of not heavily maintained, but I guess it will come back at some point. And I also check another one called Memory, which is a more modern one, which is maintained, but also only works in Linux and Mac OS. So anyway, I'll show you these. So memory profiling might be hard on Windows, but on other machines it's okay. But even without that, you can really simply in Python take any object that you have, which could be an integer, a string, a class, whatever you have, and call sys, import the sys module and get sys.getSizeOf, and it'll tell you how many bytes that object takes up in memory. So you can play with that in a notebook or on the command line. And I just ran a few here just for my own information to see how much memory does a particular Python thing take up. And what's interesting to take out of this is that Python, unlike C or other languages, like a single integer or a single float, take up more bytes than you would think because there's some overhead around them. They have some wrapping, they're actually objects with some other information attached to them. It's not as bad as it looks because Python does some very clever optimizations to not repeat. They're actually shared some of this memory, so it's not really doing it for each one. But so just by saying an integer x equals 12, you get 28 bytes. That's what I just called getSizeOf here. If you have, one thing you might not know is that integers in Python are not fixed length, unlike they are in C, unlike C or other things. You can make an integer like 10 to the 10,000, which if you did that in C, it would not work. You'd just get a floating point error, or not an integer overflow error. But Python will automatically create a larger integer storage, and so here you have an integer that's 468 bytes, but it actually can store this integer. That's sort of interesting. It's good for financial computations, or something, or I don't know exactly why it's there, but you can certainly go over the limits of what you can store in a standard integer, but they take up more memory. Floats are like, 24 bytes. A blank list itself just takes 56 bytes. If you fill the list, you get the 56 bytes plus 5 integers, so 5 times 28, and you get 104. So NumPy arrays also they have some overhead. If there's a NumPy array of length 0, still takes 112 bytes, but then you add 1,000, let's hear 64-bit ints. Strings takes all strings in Python are Unicode, which means that each character takes up generally 16 bits, and so you can add it up and you get and so large strings can eventually take up a lot of memory, but most of the time you only have to worry if you're loading a lot of data into memory, like opening a file and putting it all into one giant string, which I think we do actually in the code here. So. The other thing is, so memory allocation, this is maybe something a bit, again, deep and esoteric, but you don't have to worry about it usually in Python because it's done automatically. You're just saying x equals 3 allocates the memory. Memory is deallocated automatically also. So in C or C++, you have to remember to delete the thing, to remove it from memory whenever you've used it intentionally. But Python just keeps a count of every variable that points to every piece of memory and then runs the thing called a garbage collector in the background every few seconds, I think, or even less than that. And if it sees reference count 0, it just deletes that memory. So if you watch the amount of memory used by a program you have, you can see it will go up and down because it'll smartly, but there's some things that can go wrong here. It's quite smart. It can even find circular references and things like that. You can explicitly delete memory if you say del a variable name that removes the variable or the reference from memory and also tells the garbage collector now I can delete it if nothing else points to the same memory that this variable started to. So you can sometimes force things to be deallocated. You almost never need to do this though. This is just in cases where you're really, really worried about using too much memory. So what I want to show you is a quick, another demo here of, I can find here it is. So this one's in the memory allocation one. Where was my kernel here, which was the optimized example, I think. Doesn't really matter, this one doesn't use any library functions. But I just wanted to show you how memory allocation works because it's sort of nice to know what Python, and this is basically the same as a lot of other languages. So here I have just a stupid function that has a global variable, it calls a function, makes some memory, prints some information, and then I call this function and I print done. Really simple. You learned about debugging the other day very briefly with Max, so I'm gonna actually run this as something that, again, this is sort of a neat thing. There's this little button up here that lets you turn on the debugger. And so Max was showing how to use the debugger from the command line, this PDB, but actually there's a graphical debugger built into Jupyter, which is quite nice. This makes it easy to see. Let me close this, make it give you a little more room. And what you see is you have variables in memory, and you have, I'm gonna actually do a % reset, because that will clear everything out of memory. Yes. Now you see nothing, so right now nothing is in memory, and nothing is being called. And now I'm in the debugging mode, so I'm gonna actually put a breakpoint here, so I can just click there, and I'm gonna execute the cell, and now we can watch how the program is executing. So we're stopped here at the breakpoint, as you can see it lit up. Right now there's no memory there, so I can step to the next statement, and now my var has been allocated, so my var is in memory. I'm gonna step to the next statement, that just defines this function, so technically now there's a function defined. But now I'm gonna call the function. Let's step into that function to see what's happening. So now I'm inside my func, and the first line that it does is creates this x equals list. And if I look here, right now there's nothing locally, and there's still the global variable of my var there, but the local variables are empty. So let's step over that statement. Now x has been allocated, and I have x, which is a list of a bunch of elements. You can actually look at it here, which is kind of nice. And then when I go to the next statement, which is print, we return from the function and we get back to here, and notice x disappeared. So now there's no local variables, we only have a global variable left. So x got deallocated because Python realized that there's no longer this x, we exit the function, x is no longer pointing to this list, so it removed this memory. So that's how just in really low level detail how this stuff works. But what happens if you return a value from the function? So here's exactly the same thing. I think I can stop the debugger. How do I stop it? Let's go with that. I'm gonna do the same thing. I'll just put the breakpoint here and run execute. Now let's step into the function here, and we see the same thing. We created our x, we printed it out, and now we're returning it. And one thing you'll notice is that we return, and now there's another variable here, y, which is actually pointing to the same memory that x was pointing to. So now it's in global memory, and that hasn't been deallocated because there's two things this was pointing to the memory. We deleted x, but we returned it, so y is now pointing to the same memory, and it's there. I point this out because this is where memory problems start to happen, where you forget that you're keeping things in scope somewhere, and you build up some large amount of memory. You can accidentally forget. In this case, it's nothing, no problem. But as soon as the program exits, this would get deallocated. But it's very easy to then forget that you have something pointing to memory. This is just to show you can explicitly delete variables if you want to see that. So I'll do that quickly. If I run that, so here the same the same code. I called my, I won't go into this function this time, so now y has been allocated. I now create a reference z equals y, so I didn't create new memory here if you do this. It'll show them both as memory, but if you actually look at these, they have the same, they point to the same place. You can call ID and say ID of z equals ID of y, and it'll show you that they point to the same memory. So that's okay. And then if you step over, okay, I set an element of z, for instance. Because these are pointing to the same memory, if I print y now, you'll see that the fifth element of y is actually what I set the fifth element of z to. So this is another pitfall of Python and C and C++, that if you have two references to the same memory, this is not a new variable, it doesn't make a copy here, it's really the same memory. So if I change z, I change y also. So this is a place where bugs get introduced, but also a place where you can end up blowing up memory. I can delete y, for instance, so now y is gone, so you can see y is gone out of my list here, but z is still there. So if I print z, it's still there and it's still the same value because there's still the garbage collector knows that, okay, z is still pointing to it, I won't remove it. And if I print y at this point, it should give a name error because y has been deleted. So the reference is gone, but the memory is still there. So then here's a really bad example where I have circular references. So here I created an x and a y, and I appended y to x and y in x to y. So now you have in principle, an infinite list because it's a recursively infinite list. So inside x you have y, and inside y you have x. And let's see what actually happens here, because I'm going to turn off the garbage collector just so we can see what happens. So that's a way you can turn off the garbage collector if you want for a moment. So I have x is in memory, and it looks like a list. It looks short, right? Then I put y in memory. That's also a nice little short list, A, B, C, D. But now I'm going to put x to append y and y to append x, and we should see basically this is an infinite data structure now. It goes on forever. So this is somewhat dangerous if you were to loop over this. You would loop infinitely, if you loop recursively at least. And I can manually call the garbage collector, and that will tell you how much memory was released here. And I think this, or what it actually deleted there, nothing, because nothing's been removed. Oh, sorry, but now let's say I delete the x variable, but now we still have it inside that circular reference. And now if I delete it, it did actually remove, I think that was the size of, I don't know, that's probably just the size of the reference. And then we delete it, and it tried to collect it, but couldn't, because if you look, there's still the memory in that doubly linked list, but then the garbage collector should be smart enough at the end that it removes all the memory that was allocated. So it can detect these loops and things. But anyway, these are things you have to be worried about, that you might have made this happens quite frequently if you have very complex code where you accidentally realize you have a reference to something that also references back to something else, and then the garbage collector cannot delete it by itself. And so you end up blowing up memory because every time you add to it, it gets larger and larger, and you never delete all the references to it. Anyway, that's, again, very esoteric, but I thought it was interesting to show. Also to show how Python interpreting actually works. And this brings me to a final mention. I said there's something called a memory leak that can happen. This is something that does happen. I've seen it in a lot of code that students and myself even write, where you forget, again, like in this case, that you keep a reference to some data somewhere, and that data keeps growing in size. And this can happen accidentally, especially with global variables. So in this little example I give here, I have a global variable called global state, and then in my function I add stuff to that global state, and I forget about that. And if I call that function many times, you can see that the memory size keeps growing, and that's bad, right? Because that means that if you run this program for a much longer time, eventually it gets bigger and bigger, and then you run out of RAM and the whole thing crashes. You can even crash your computer this way by just using too much memory. You're allocating memory continuously, and it never goes down. So if the garbage collector is working correctly, you'd see up, down, up, down, up, down, and it would stay eventually fairly flat. But if you ever see memory usage increasing, and I'll show you how you can measure this, that's bad. It's a bug in your program. There's a couple ways you can check memory usage. So there's this, I think it's already added to your environment here, but you can try Pixie add memory profiler into your scripts if you don't have one. Then you do Pixie run mprof run, and then again, Python script or whatever, or you can run pcoffee here. And that will run the code and sample the memory every fraction of a second. and then you type pixie run mprof plot, it'll give you a plot. So this is just from an example I had showing how the memory evolved over time. And like I said, if it looks flat, it's probably fine. If it's always increasing, you have a problem. Just like the other profiler, you can also do like line profiling with memory profiler. It's a bit of a pain. You also have to put this decorator on top. I'm going to show you an example of this in the notebook later on. But then it'll show you for each line of code how much memory was allocated on that line. That's another good way to check if you're using up too much memory somewhere. So then you can do this in a notebook the same way as the other one. Instead of time it, you have memit. And again, you have to load this memory profiler extension. So and then also a full-featured report like the profiler, MP, instead of prun, you do MP run. So I'll show this in just now. I think now it's demo for this. So if we go back to our, I know this is a lot of information and very complex, but like I said, most of the time you'll never need to use this information. But let's see, let's go back to our profiling example, because now I want to know all those implementations I did of the Gaussian smoothing code, do they use more or less memory than the others? Because this might be a reason why you might choose one over the other, because your laptop or your machine has less RAM on it and you don't want to crash it when you give it a very large image. So here I just loaded the memory profiler extension, and then I have this memit function which also has the -o. So I do it almost exactly the same as I did with the perf. I run all I didn't run all the functions here, I did 4 of the most interesting ones, I guess. I should try it with the Numba one as well. I guess I could add that there, but here I'm just running all at once the profile for each one, and then I make a little plot function and we'll plot it. So let's see how these fare. Okay, close this, by the way. This doesn't go anywhere. And this, again, will take a little bit of time because I think memit also runs things multiple times to get statistics. And it also is attaching the memory, the little bit of code that checks for the memory also adds a bit of overhead, so it's never as fast as when you run the code normally. Let's see, my CPU is not doing too much, but it's still running. Oh, I realized I gave it, yeah, this is also why. So by the way, memory usage, in my examples above, the memory usage is actually pretty small because I made that cutout image, but here notice I'm running it with image full, so this should be a lot slower. This is why it's taking a long time, because this first one running with loops on image full was extremely slow, so this will take, maybe I should have switched back to using the image again, but then the problem is if you don't use something very large for this, you just don't have enough, it doesn't allocate enough memory to be noticeable compared to other stuff that your system is allocating. So it's good to try it on a very difficult problem. So if this doesn't, oh yeah, okay, no, it worked, okay. So the first one was probably the slowest, okay, now it's running the others. And you can see here now, this is the amount of memory used by the different implementations. And you can see that the loops one uses essentially, okay, some low amount of memory. And it's a bit hard here, this is always relative memory, so it uses very little. NumPy outer loop actually uses very little. The NumPy no loops though uses a lot, right? That's because inside that I had to allocate this 4-dimensional array, and that actually uses a lot of memory. So that thing is very inefficient. That's one of the reasons why it was slower. And the SciPy version, of course, uses basically no memory. We could try this with the others too as well and see if they're better. But this is another reason why. So it's not just looking at performance. One of the reasons, though, the reason why this was not as performant probably is because it's allocating a lot of memory. And in this case, it's allocating about, again, I guess this is in, what should I plot? This is in bytes probably, or megabytes. I have to see what the actual, but probably megabytes, because this is, yeah, so this is, or maybe it can be gigabytes. Oh yeah, no, it's probably megabytes. So this is yeah, it must be 1.4 gigabytes, probably it allocated around here, it's 1.5 gigabytes or so. So if you're running this on a computer with not much memory free, this could be a problem. Or if you used an image that was, instead of 1,000 by 1,000 pixels, used one that was 10,000 by 10,000, you'd probably crash your computer. So with that one, so you probably want to keep with one of these other implementations. There's this other package called Memray, which I thought was quite nice. I only just tried using this yesterday, but it gives you sort of like that what's it called, snake viz. It gives you a little visualization also of memory. So I just tried it here for, okay, maybe I shouldn't, oh, this is the NumPy version, so this should run fast. Oh, sorry, this is called smooth NumPy, no loop. What did I call it above here? Outer loop, right? Change the name here. And it gives you this report that's a bit like, so here it's not very interesting because that function, it's only one function call, but if you look at the graph, or where's the button here, memory graph, it shows you over time how much memory was allocated, and you can see that it's fairly flat because that one was not too bad. And you can do that with the other ones. This is the no loops one, and if you look at the, notice there's a big jump memory graph. You can see it went, it allocated quite a bit of memory and then dropped down at the end. So that was this extra memory that got to be done in the loop. And then we have one, this was the, oh, that was actually the same one I just did before. So anyway, that you can see different, you can compare different ones and see which ones use more memory. Here's that example I had of the memory leak where I had some global memory and I have a leaky function that then adds stuff to this global memory each time. Here it adds a 1,000 by 1,000 array every time I call it, and I call it 100,000 times. So this is a bad example of very bad code you wouldn't want to do. But if I put this memory flame graph, you should be able to see that. And so here, if you look at the memory graph, you can see it just went up. So it went from 0 to 8 gigabytes in a few seconds. So you immediately see there's a problem, and you should redesign your code or delete things, or don't store things in a global variable. Okay, so that's memory profiling. There's a lot of different ways, like I said. You can try this again if you want to try running it on pcoffee, like we did from the command line. You can see the example, and that might be a nice thing to try. But I'll show you in a moment. There's another task I have set up for you. Okay, and I think I'm almost done with the presentation, actually. So there's another option which actually I find I could not get to work this time. And the last time I gave this talk, it worked. And I think the latest version, again, this memory profiler is no longer maintained very well, and I think it's somehow broken. So normally you would be able to also, just like in the profiler, you could set an option PDB mmem, and when you've allocated more than 100 megabytes, it should drop into the Python debugger and tell you where that happened. And that used to work, and now I tried it and I could not get it to work again. But what you can do, though, is just still get the analysis results. So here, just like the C profile, you can, even without that option, you can run like pcoffee and see how it, see what it does. So let's actually, let me cut and paste this, because I'm going to definitely, I'm definitely going to forget how to type this. So this is what I want to run. And let's go into my, if I can find my, I have too many things open at once. This was my, yeah, here it is. So in my pcoffee analysis, let's make this full screen so you can see it a bit better. I'm going to run python-m memory profiler. I'm going to get rid of that PDB thing because I think it's not working for me. At least try it for yourself. Maybe it works. Maybe on Linux it does, and not on macOS. This is most likely. But I'm going to run my pcoffee CLI. I'm going to run with analyze data, whatever, the same thing as before. Show rankings, and this should do something. Oh yeah. What didn't it like? Oh yeah. Did I not install? I'm in day 2 solution. You have to have Pixie add memory profiler if you haven't put that in. I have it in my other repo, but not in this one. And now if we run it, no module named. Oh, do I have to be? Edit it, right? That's strange. Oh, yeah, no, wait, hold on. I'm in, just make sure it is Pixie add. I think I added it to this correct directory. Let's see. No, maybe not. Okay, now it's there. And now if I do pick, I got Rex up here. Pixie run. Let's just run this Python, blah, 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 this stuff. Let's see if it works. I think I installed it in the wrong. Yeah, okay, so now it's running pcoffee as normal. It should have created something. Let's see. It did not. Why did it not? Yeah, I have to check now why this is not outputting. Oh, I have to decorate. I probably have to decorate a function inside it. Okay, I'll show it. There's another example I can show you, which is simpler. But yeah, you can try this, but you'll have to go in and I think decorate one of the functions with memory profile. Otherwise, it won't show a result. However, in this demo here, I made, in this other directory, in the lectures one, I made a little function called mem.py. And that one imports memory. This is what you would have to do in your code to check it. From memory profile, import profile, and put this at profile somewhere in your code, maybe on the main function, and it will then decorate that one. So here we can do pixie run, again, we're Python. Actually, I don't even think I have to load memory profile here because it's loaded inside the script, and that would give you, let's see if that works. Yep, and now when it exited it, it gave me this memory profile of the function that I decorated, because it doesn't do it for unlike the profiler, it doesn't do it for everything, just for the things you decorated. It's always by line, and you see by line where I allocated memory. So here I did I allocated an X and a Y that are 10,000 elements. I just did I slept for half a second just to give it some time to do it. Then I do some math on those things. I make a two-dimensional array from that. I did a bunch of crazy things, and you can see making a two-dimensional array allocated a ton of memory. Adding one to it also allocated a ton of memory. You can see where memory is being used. Here, these use very little because they're only 15 megabytes or something like that. You can also do something like this. Since you have the memory profile installed, I told you there's this mprof run, and do the same thing. Python. I think you can do run -- Python, and then what was that called? Mem.py. Or you can type Python there as well. It doesn't matter. And it looks the same, right? It did the same thing, but now it should have output something called memprofile here, .dat. And if I do pixie run mprof plot, I should get something that pops up somewhere. Maybe I have to not have this full screen there. Yeah, and so here is the plot of running that piece of code, the memory allocation over time, and you hear I had this in the code. I slept for half a second, and then it allocated more memory. I slept, and then at the end of the code, it deleted all the memory. So again, this can be used to see. And the peak here was at about 1.5 megabytes. So that's interesting. And so you can see if you get too large, you can see where the peak happened at what time during your code. And if you run it multiple times, it'll plot all of them on top of each other, et cetera. And you can do mprof has a bunch of other options like listing all the different measurements you've made, and you can do mprof peak, and it should tell you that the peak, without plotting it, it'll say the peak was 1585 megabytes. So it's a good way to check how much RAM your programs run. Technically, it doesn't even need to, this can work on things that are not Python. I think you can run anything after mprof. I think it should work, because it's just sampling the memory. Okay, so that's the rest I kind of decided to skip because I think it was too much detail to go into. There's already a huge amount of detail, and I think this has gone over the heads of a lot of people. But the idea is that you want to be able to identify where there's problems in your code a lot of times and then fix them in some way. How you fix them depends entirely on your code or what the actual problem is. But I have a little thing for you to try though. So like I said, the solution, the pcopy thing is way too fast and doesn't need any performance. So I broke it. So if you fetch the day 2 solution slow branch and switch to that, it's the same code, but I've added some bad code into it. So obviously, if you look at the git diff, you'll see exactly, you can find it. So don't look at the git diff. But without looking at the code or the git log, try one of those profiling tools and see if you can find where I slowed down the code. And you'll see that it runs like, it's not wildly slow, but it's instead of in a fraction of a second, it runs in like 5 seconds or 6 seconds, and you can see if you can find out where I broke it. So that's a fun, maybe not fun, but a way you can try playing with this. And then the other thing is you can try, and there's many ways you can do it. You can do it in the Python in a notebook, or you can just run one of these command line tools for the profile and then for the memory profile. And see if you can identify where it is. The other thing you can play with if you have some time or interested is to look at those examples I made in the of the Gaussian blurring and see if you can try adding JIT to different places and see if you get a better performance than the ones that I showed. Okay, so our questions or we ended a little bit early, so we have time. We have 20 minutes now to try that, and then otherwise. Otherwise, then we can start. You can start with the activity. Yeah.